let's try to define this NS operation in Haskell. So we already have this data type definition for less than. Okay, we may try to start with a type definition like this. So if you give me a natural number and a vector, and I also want to prove that this some natural number is less than n. But the problem here is that this natural number should be the value of this type. But if we write it like if we write it similar as if Idris, we will get a type error. So and the type error says here we expect the type, but M of type net has kind of met in this type signature. So what does this mean? This means so in Idris, here this M is the type of this function, and this net is the type of this function, and M is the value of type net. But in Haskell, here the type in this arrow is M, and the kind of M is net. So it's like we have three different kind of things. So we can have a value which of some type and this type of some kind. So in Idris, when you say here this M is of type net, you actually say that I have a value which is this M and it has this type net. And in Haskell's type signature, like how it interprets this type signature is that you have a type M and this M is of kind of net. So, however, this function, this arrow expect a type, which is actually of kind of star. So, but you give it some type of kind of net. So it gives you this type. This arrow says in the type signature, this one actually has kind of net, but I expect a type. So this means, unlike Idris, we are not able to give this value a name. Then there is no way to construct or prove that this M is less than N. So what we want is something like this, like in Idris. Since we have no way to give it a name, we cannot say that this M is less than N. So this definition won't work. And the way to solve it is we need singleton types. So here I have another definition which looks very similar as net. And the only role of this definition is to bring this net to do exactly the same thing we did just now, to give net a name. So this S9 takes a net and returns your type. And S0 is of type S9 0, and S star is of type S9 M and returns your S9 stack M. So we call S9 is a singleton type because every data constructor has every type has exactly one non-boundary value corresponds to it. So for example, S0 is the only inhabitant of the type SNet 0. So if you have SNet 0, then its value can only be S0. And S sub n is the only inhabitant of this type. So basically in this type definition, we have this relation. So this SNet is actually isomorphic to this net type, which means we can write a function that converts between SNet and the net and back forth. And this 0 is actually isomorphic to the original 0 in the original data type definition. And this suck S sub with this SNet n, which is the value, is actually isomorphic to this suck n. So this is why we call it a singleton type, because you are actually define an isomorphic data type between this new data type and the original net type. And we can use the definition of SNet to define this nth function. So because SNet takes the net as its value, so now this net has a name m. And if it is this, and we can tell it to carry a proof that m is less than m. And then we can define this ms. So if it is S0, then we will just return the head of it. And if it is sub m, then we will have we will continue with this proof. So now this definition looks like what we had in Idris, right? So just now in Idris we have So this definition is what we had in Idris just now, and now we have a very similar definition as we had in Idris. And we can rewrite the previous example 2 and example 3. Here we will provide those evidence explicitly. So the first element of 1 to 5 is 1, and the second element of 1 to 5 is 2. And we can never construct a proof if we want to get the head of an empty vector. So here we can never construct such proof that that 1 is less than 0. But providing this kind of proof could be tiresome, because here we only show that 1 is less than 5. But maybe we want to show that 999 is smaller than 1,000, and then we are going to provide a very long list with 999 in the one base. So we want a way to optimize it. So in Idris, the way to do it is you will use this special notation, that's this curly brackets. And if you put a curly brackets and over here, so then every time when you call this function, it just will try to figure out a value for you. So now you can write this example 2 and example 3 without the explicit proof, and it just will figure it out for you. Now how can we do it in Haskell? So the way to do it in Haskell is we are going to use type families again. So remember that type family gives us the power to define type level function. So here, this type level function returns a boolean. So when we say that, I say that yes, 0 is less than any number which is larger than 0, and it will give me a true. And no number is less than 0, so it is false. And whether this sub m is less than sub m depends on whether m is less than n. And now I can write the nth function by using a constraint. So here I'm use this Twiddle notation tells GHC I want an equality constraint here. So I say that I want m is less than n to be true, and then I will just use this number m and the vector of less n. And in this definition, I no longer need to pass the proofs. So if we rewrite the previous example before, here you can see that we no longer provide the proof here. So do you have any questions so far?
What error does GHC give if you try and, like in the previous example, if you try to index too far, what does it say?
You mean this example if the index is too large?
Yeah, with the constraint. What does it tell you?
Okay, you can try it out. Well, it says cannot match type false with true. Yeah, because because here this 1 is less than 0 will evaluate to false, and here you expect it to be true.
That means the false, the type false is a type.
Yes.
Yes. So because this is a type level function, so it's always return a type, and here this boolean is actually a can.
If you
The boolean is what, sorry?
It's a can.
Oh.
if you turn on the thing where it checks if you've matched all the cases, is GHC smart enough to know that this is a total function, or will it tell you that you're missing some cases?
Yeah, that's a good question. Do you remember the flag name?
No.
Okay, I can just turn out all the warnings. Can stop it all.
Oh, F warn incomplete patterns maybe?
F warning.
Yeah, it seems like F warning could pick up.
Semicolon. That's good, right?
No, not warning, just warn.
Just warn.
Yeah.
Okay.
It work?
Yeah, it's work.
Cool.
Yeah, I think when I check this expression, just to bring this constraint in scope and then it will identify it. And do you have more questions? And do you have more problems? Like, are you satisfied with this encoding? Yes? Okay. So one problem we have is, like, we have two definitions for class. We have one term level definition for class, and we have the type family definition for class to do type level computation. And we have one definition for net, and we have one definition for SNet, right?
Just don't play Haskell. Don't play Haskell.
Yes, exactly. So here we are repeating everything, right? And you can imagine when you have more things that you want it to be dependent type, you are going to repeat more things, and there are many duplications. And the first question we will ask is why? Why do we need this? Why do we have those kind of duplications for every type of function? So the reason is, so in GHC, like runtime value and compile time types are separate things. So in order to express the dependency between a runtime argument and a compile time type, we will need to use template type families and singleton types. So you see just by slightly change the original definition to make it work. So the question is, can we do vector? And yes, we can. So the answer is to use template Haskell, but someone already did it for us. So I'm going to introduce the singletons library. So the singleton library is introduced in one paper in Haskell 12. So this library uses template Haskell to automatically generate those kind of duplicated things for you, like the singleton types, like the type families, and those kind of types. So we can rewrite this example using singleton Haskell. So here I turn on more language extensions, and I import this singleton library. And now this is how I will write this dependent type program in Haskell. Here, this dollar and this tuple is the syntax of template Haskell. So this is to tell. So template Haskell is just a way to do meta programming in Haskell. So you can write some program that operate over the other program. And here we define this net definition and the class function in the term level, and this less than also in the term level. And we tell template Haskell that I want this singleton thing to generate something for me for this definition. So what singleton will do is, so given all these term level definitions, it will generate the singleton types for you, and it will generate all these type families for you. Now, you can see in this file, I never defined this type family class, and I never defined this less than. But because I use the singleton library, so I cannot just write, I can just use it because I know it will be generated by the singleton library. So now this code looks more like what we have in Idris, right? Because we don't need to define type families and those kind of things. So singleton library is useful for writing dependent type program in Haskell, and it can generate those kind of boilerplate code for you, and you can write more Idris-like code in Haskell. And do we have any questions so far? Are you satisfied with this library?
can I say that in summary, for the current GHC implementation, we can do some simple dependent type Haskell program using all the extensions
Yes.
you mentioned.
Yes.
That means, or if you are sick of writing all these boilerplate, even the singleton is available in the package.
Yes.
Could you put it, please share your GitHub source code?
Yeah, I will
Oh,
put
yeah.
it in my data.
Oh, okay. Because I definitely, sure, I forgot anything. And I need to refer to the source code.
Okay. Yeah.
You know, with Idris's, the whole polls in Idris, do you think we can extend this with, to make it even better?
So in Haskell you have the type holes, right? The underscore,
You mean partial type signature?
not the underscore, like the type hole.
Oh, yeah, underscore.
Yeah.
Yeah.
Would that?
Would it work? Like
Yeah.
Idris style?
I don't so.
I mean, it won't work now, right? But
Yeah.
do you think there's like a lot of work to make that work, or is this like a little bit?
Yeah, I think there is indeed one paper in Haskell Symposium this year, like to make a suggestion for candidates for this course.
Oh.
Yeah, but I think it's not implemented yet.
Yeah.
Yeah. So to make everything like the program I wrote work, we are actually use a lot of language extensions, right? So in this example, I only use 8 language extensions. Yeah, only 8 because we have lots more extensions. If you have more like fancy programs, and the problem is there is no unified meta theory for this extension. Basically, for each extension, you will find like one paper for it, and in that paper, it introduced this extension, but it may not introduce well, like how it interacts with other extensions. And the duplication still exists, right? Whether written by us or generated by singleton. This is how dependent type work in Haskell. We always have this kind of duplications. And even though like researchers work so hard to make every extension work, there are still many restrictions on those extensions. So, what can we do better? So the answer is yes. So we want to have dependent Haskell, like truly dependent type Haskell. And the goal is to extend GHC with 4 spectral dependent types, and which we want it to be compatible with the current implementation, and we can then simplify and unify those kind of language extensions. But adding dependent types to GHC is very difficult, right? We have like so many modules in GHC, and there are some mutual dependency and somehow something. If you modify one thing, you are going to affect like just everything. But luckily, so GHC incorporates several compilation phases. So it is possible to change like one phase in the middle of this compilation line and without affect other phases. So as one step towards dependent Haskell, the first goal we have is to have dependent core. So we want to make the core language of GHC dependently typed, and with dependent core, maybe we can lift the dependent type power into the source Haskell. And if you are interested in this topic, there are some discussions you can find in this Haskell wiki. So this is an ongoing project. And so the original plan of this talk is to talk about correction quantification, which I did with Richard Eisenberg together this summer. But because that is too technical, so we just changed it to a more beginner-friendly tutorial. But I will give you a big picture of how things work, how things is going in dependent Haskell. So for example, this is the word of Haskell, like everything you want from Haskell. And now we want some part of it to be dependent Haskell. And as a first step towards dependent Haskell, as I just mentioned, we want the dependent core. So we want the core language of Haskell to be dependent type first. And because of the meta theory of dependent core, it turns out we want homogeneous equalities. I'm not going to explain what is homogeneous equality to you. And then to implement homogeneous equality in GHC, we find that we want coercion quantification. So this is the step we are now at in GHC towards our goal. So we are still at very early stage of this in this whole picture. And if you want to know more about coercion quantification, it is so we have a talk at Haskell Implementers Workshop this year, and you can find like extended abstract and slides of coercion quantification in my homepage. You can also find these slides and the code sample I used in my homepage. I think that's all. Yeah. Thank you. So do you have more questions?
I mean, I have one, but I'm not going to ask it. It would be, what is coercion quantification?
Well, this is not very easy to explain, so
I assumed as much.
I will recommend you just check
Yep.
my extended abstract.
Sounds like a mathematic term.
I would think so.
Not exactly. So, so you know about polymorphic type, right? Like the for all A, like A to A. And coercion quantification is we have for all C, where C is a coercion. We quantify over a coercion variable. This is a coercion quantification. If you don't understand what I'm saying, that's fine.
What do coercion variables look like in core? Like, what does that represent? Do you have a coercion variable?
We already have one example in my code. So this is equality constraint. And in core it would be, it's a function, not a quantification, but this is a coercion variable. And the coercion variable is the proof of this equality. But here it's just a function. We already have coercion function in core, but we don't have quantification over coercion variable.
Do we quantify over the two variables on the sides of the coercion, or which part of it are we quantifying?
Which part of it?
Yeah, I guess I don't know if that's the right question, but like, what does it mean to have different coercion variables that we're quantifying?
What it means to have different coercion variables?
Yeah, like if you quantify over a type, that means that your function has to work with any type, right?
Yeah.
But what does it mean to quantify over a coercion? Like,
Oh,
how can you have
okay.
different?
I understand the question. So, you mean if we have this kind of coercion, why do we want to quantify over all coercion variables? Yeah, the reason is not to quantify over all proofs, because all proofs are just, if you have proof, then just a proof, right? Everything are similar. The reason is we want to refer to C in this T. You can interpret function as anonymous dependencies, right? But here we want explicit dependency because we want to refer to this C in this body T.
And we can't, right now we can't refer to
No,
the
we
coercion.
can't.